So can the exact same Wi-Fi technology inside your smartphone or sitting on your desk right now as a home router actually bridge a 50-kilometer gap? I mean, it sounds a little bit like science fiction, right? We've all been there. You literally just walk into the kitchen and boom, your connection drops because the router is in the living room. But today, we're going to find out just how far this standard everyday tech can actually be pushed.
Welcome to This Explainer. Today, we're diving into a truly fascinating article from Haber, and we're going to explore how 90s hackers, armed with absolutely nothing but soldering irons and a whole lot of patience, alongside modern internet service providers, pushed standard Wi-Fi to extreme, totally unintended limits. We are talking about stretching a signal that was explicitly designed for your cozy living room across entire cities, over mountain ranges, and across vast landscapes. Honestly, think of this explainer as a boss rush video game, where we have to defeat a gauntlet of physical, environmental, and legal hurdles to make this epic 50-kilometer journey a reality.
All right, so here is the 50-kilometer obstacle course we have to defeat today. We'll start with the directional antenna secret, then we'll look at geometry, specifically Fresnel and curvature. Next up is the speed of light, then nature and the law, and finally, we'll answer the big question, is it actually real?
Okay, let's jump straight into level 1, the directional antenna secret. I absolutely love how the source article breaks this down with a perfect metaphor, the light bulb versus the flashlight. See, your standard home router relies on an omnidirectional antenna. It behaves exactly like a bare light bulb hanging from the ceiling. It just spreads its radio energy evenly in all directions to flood a single room. But if you want to go 50 kilometers, you need the flashlight. You need a parabolic directional antenna, which is essentially a satellite dish. Instead of wasting all that energy spreading it out, it concentrates the radio waves into a super tight, narrow, highly focused beam. This allows an otherwise weak, standard 100 milliwatt signal to achieve massive gain. And what's really cool is that a narrow beam basically acts like blinders on a horse. Because the antenna is only listening in one highly specific direction, it physically rejects all the outside noise and interference coming from the sides. It's all about focusing the power you already have.
Moving right along to obstacle number 2. Geometry, specifically Fresnel and curvature.
Now, you'd probably think, hey, if my two antennas have a direct visual line of sight, we're golden, right? Like a laser pointer hitting a target. Well, actually, scratch that. Radio waves are way messier. Enter the first Fresnel zone. It's this invisible, elliptical, cigar-shaped volume of space stretching directly between the two antennas. Because radio waves don't just shoot straight, they kind of bulge out in the middle. If indirect radio waves bounce off nearby surfaces within this cigar shape, they get delayed. They're phase shifts. And when those delayed waves finally reach the receiver, they crash into the main signal totally out of sync, creating destructive interference. They literally destroy the primary signal. To stop this on a standard 10-kilometer link using a 5 gigahertz frequency, you need at least 12.25 meters of pure vertical clearance all the way across. So if you're in a city full of 10-story buildings, your antennas need to be 3 or 4 stories higher than all of them just to keep this invisible cigar-shaped zone totally clear.
But wait, there's an even bigger geometric problem than buildings, the literal Earth. The author of our source article makes a great joke that radio engineers are never flat earthers, and well, this is exactly why. Because the Earth is a sphere, the ground literally curves right up into your line of sight. Over a modest 10 kilometers, the Earth bulges up about 2 meters in the middle. But look at the math for our 50-kilometer target. Over 50 kilometers, the Earth's curvature bulges a staggering 50 meters. This is not some tiny hurdle. This means you need incredibly massive 50-meter-tall towers, or you have to rely on high mountain peaks, just to maintain a basic line of sight without the planet itself blocking your Wi-Fi.
Okay, boss number 3, the speed of light. Ever wonder how your router actually knows your phone got the picture it just sent? It uses something called ACK, or acknowledgement logic. Here's how it works. 1. The transmitter sends a frame of data. 2. It waits a strictly limited, incredibly short amount of time. 3. If no ACK frame is received back from the phone, the router just assumes the data crashed or got lost and it forcefully resends it. In your living room, the distance is just a few meters, so the data arrives instantly. This impatient protocol keeps your data perfectly safe. But over vast geographical distances, this hard-coded impatience completely falls apart.
And why does it fall apart? Because we literally hit the absolute speed limit of the universe. Radio waves travel at the speed of light, which is about 300,000 kilometers per second. So a 1-kilometer round trip takes 6.7 microseconds. But a 50-kilometer round trip, that takes about 335 microseconds. Now, standard Wi-Fi timeout limits are usually set to just a few dozen microseconds.
The protocol is simply not programmed to sit around waiting for 335 microseconds. The signal physically takes too long to travel the distance, which forces the system to panic, time out, and fail, even if the radio waves perfectly reach the other side. To beat this boss, network engineers have to dive deep into the firmware and manually hack the ACK timeout settings to account for the speed of light, literally adding microseconds of patience for every single kilometer of distance.
Next up, Level 4, Nature and the Law.
Oh man, the source details this incredibly frustrating phenomenon known as the lake curse. Imagine spending weeks perfectly aligning a connection, only to have it ruined by a puddle. Seriously, beaming a Wi-Fi signal over a lake is an absolute nightmare for radio engineers. The temperature and humidity gradients sitting just over the water cause radio waves to literally bend through the air, a process called refraction. Plus, the calm surface of the water acts like a giant, perfect mirror, causing reflected waves to bounce up and smash into your main signal. You can painstakingly set up a flawless, high-speed connection in the freezing, dry winter, and the second a hot, humid summer evening rolls around, the signal will just start heavily fluctuating and completely flatline.
And then there are the unpredictable physical changes in the environment. This quote from the source brilliantly captures the everyday, pull-your-hair-out reality of building urban radio bridges. If a house appears gradually, a tower crane will be assembled in a flash, and by Murphy's Law, it will end up exactly on the line between your 2 points. You know, trees at least have the decency to grow over several years, but a massive metal construction crane that can pop up overnight and totally block your perfectly aligned 20-kilometer signal?
But honestly, the biggest boss of all might just be the law. A lot of people think 2.4 and 5 GHz Wi-Fi frequencies are just a total free-for-all. They aren't. They are only conditionally license-free. Short-range device rules strictly limit your equivalent isotropically radiated power, or EIRP, to just 100 milliwatts, which is 20 dBm. So if you take that perfectly legal 100 milliwatt home router and slap a massive 24 dBi parabolic antenna onto it, your output instantly jumps to 44 dBm. You are massively violating the legal limit, effectively turning your setup into an overpowered, highly illegal beacon. And on top of that, in the 5 GHz range, outdoor setups almost universally require strict frequency use permits from the government.
And even if you decide to play rebel and risk it, you're facing incredibly chaotic radio conditions. Because you're operating in unlicensed airspace, you are actively competing for the exact same frequencies with thousands of household routers, smartphones, and yeah, even cheap, noisy baby monitors that can completely jam your carefully crafted signal. And amazingly, regulators actually drive around cities with sophisticated mobile tracking gear, actively hunting down these illegal, overpowered bridges just to issue steep fines and protect the spectrum.
Which brings us to our final section. Number 5, is it actually real? Well, short answer, absolutely. Take a look at this thing. This is the Ubiquiti AirFiber AF5X. It is a massive 20-kilogram ISP-grade monster of an antenna. When you manage to defeat the Fresnel zone, the curvature of the Earth, the pesky speed of light timeouts, the lakes, the cranes, and the local regulators, commercial setups using heavy-duty hardware like this have achieved staggering distances, way beyond a standard home router. By placing these hefty antennas on the very tops of high mountains, engineers were able to bridge a mind-blowing 304 kilometers between Sardinia and the Italian mainland, and they achieved consistent speeds of up to 356 megabits per second.
But get this, the absolute Guinness World Record, 382 kilometers. This jaw-dropping distance was achieved by researcher Ermanno Pietrosemoli, high up in the thin air of the Andes Mountains. And the craziest part? Using standard 802.11 technology, he managed to successfully deliver about 3 megabits per second over a 382-kilometer gap. It brilliantly answers the question we started with. Yes, standard Wi-Fi protocols absolutely can span mind-boggling distances, provided you secure the ultimate geographical high ground.
As the source points out, commercial internet service providers often rely on these exact types of radio bridges to beam internet into rural areas where laying fiber optic cable is just too expensive or logistically impossible. Some of them operate entirely legally, while others operate as rogue pioneer nets, basically just hoping they don't get caught by the regulators driving around below them. So I'm going to leave you with this provocative thought. With thousands of these overpowered rogue radio bridges currently cluttering the skies above our cities, constantly shooting invisible data right over our heads, is this chaotic, unregulated laser grid of Wi-Fi just a necessary evil for modern connectivity? Definitely something to ponder the next time you're looking out over your city's skyline.